China just launched a game-changing satellite that never stops watching. Today, we reveal how GaN technology and the Gallium Gap give Beijing a massive strategic edge.
But the real weapon is not in orbit. It is the gallium supply chain America cannot break.
Beijing holds the high ground. And this is bigger than chips. Welcome to the Gallium War.
Imagine a single satellite hovering 36,000 kilometers above Earth, fixed over the same spot day after day, with visibility over roughly 1/3 of the planet's surface. This is not science fiction. This is Lutytance 401, also known in defense intelligence circles as Lutan 401, China Geosynchronous synthetic aperture radar satellite launched in August 2023. Unlike conventional radar satellites that orbit in low Earth orbit and pass over a given location only a few times per day, this satellite stays put. It maintains persistent observation over vast regions, including the Asia-Pacific, supporting the monitoring of ships, aircraft, and ground movements through clouds and darkness in most weather conditions. The United States has studied geosynchronous SAR concepts for decades, but has not yet deployed an operational system comparable to Lutytance 401. Chief Master Sergeant Ronald Lurch of the U.S. Space Force Space Systems Command has acknowledged that this satellite enables persistent surveillance over strategically vital areas. When coordinated with China's broader constellation of reconnaissance assets, it represents what military analysts describe as a qualitative leap in tracking and targeting capabilities. The implications for regional security, particularly in the South China Sea and around the Taiwan Strait, are significant and deeply concerning for American defense planners. To understand why this satellite is such a breakthrough, we need to talk about the brutal physics of radar at extreme distances. A typical radar satellite in low Earth orbit sits about 600 kilometers above the surface. Lutytance 401 sits at 36,000 kilometers. Radar performance degrades dramatically with distance because both the outgoing and returning signals weaken over long ranges, making SAR extraordinarily demanding in terms of transmitted power and antenna performance. The math is unforgiving. Without extraordinary power generation and transmission capabilities, a geosynchronous SAR satellite would struggle to produce usable imagery. This is where gallium nitride enters the picture. According to reporting on a study from China Journal of Microwaves, researchers associated with the Sine Institute of Space Radio Technology described the use of GaN high electron mobility transistors and solid-state power amplifiers for space applications. Each individual amplifier can reportedly generate 800 watts of microwave power, and when combined across the satellite active electronically scanned array, the total output exceeds 18,000 watts. The reported power added efficiency reached 50.3%, which would be remarkable for a space-based system operating at this scale. These figures, if accurate, explain how China solved the power problem that has made SAR so difficult to achieve. Gallium nitride is not just another semiconductor material. It represents a fundamental leap beyond silicon and gallium arsenide in terms of power density, thermal tolerance, and efficiency at microwave frequencies. GaN can handle significantly higher power levels per unit area while maintaining performance at the frequencies required for advanced radar systems. This makes it indispensable not only for space-based SAR, but also for active electronically scanned array radars on fighter jets, electronic warfare systems, and next-generation defense platforms across every domain. The material has become a cornerstone of modern military electronics. The satellite reportedly uses techniques to synthesize multiple microwave signals to maintain stable performance at extreme range. Without GaN efficiency, the power budget and thermal management challenges would likely make the entire system unworkable. China has also been advancing related semiconductor technologies. Chinese researchers have reportedly developed cooling innovations that can boost GaN-based radar performance by reducing thermal resistance. In parallel, scientists are investigating gallium oxide compounds as ultra-wide bandgap semiconductors that may handle even higher electrical power in future systems. These research directions suggest Beijing is not content with its current lead and is actively extending it. Lutytance 401 is not operating in isolation. China has also deployed the SuperView Neo-2 satellite pair for high-resolution Earth imaging. These satellites serve dual-use purposes, supporting commercial applications while providing capabilities with strategic value. Together with Lutytance 401, they form part of a layered surveillance architecture that combines persistent wide-area coverage with higher-resolution spot imaging. This constellation approach means China can maintain continuous observation over strategic regions while retaining the ability to focus on specific targets of interest. The civilian applications, including disaster response and agricultural monitoring, do not diminish the strategic value of these systems. When a satellite can support the tracking of individual ships across thousands of kilometers of ocean day and night, its military relevance is clear. The combination of geosynchronous persistence and advanced radar capability gives China a unique position in persistent geo-SAR surveillance that no other nation has publicly demonstrated. This is not to say other nations lack surveillance capabilities overall, but the specific combination of geo-orbit with SAR imaging represents a distinct technical achievement. Here is where the story shifts from engineering achievement to strategic vulnerability. Gallium is not mined independently. It is extracted as a byproduct of aluminum production, and China, as the world's largest aluminum producer, dominates global primary gallium output. Estimates suggest China accounts for roughly 95% of refined gallium production worldwide. This is not merely market dominance achieved through superior technology, it is structural dominance rooted in China control of the upstream aluminum industry, which makes gallium production economically viable at scale in very few other places on Earth. China began tightening gallium export controls in 2023, and by late 2024 had effectively blocked exports of gallium-related products to the United States for certain applications. The U.S. Geological Survey has flagged gallium as a critical mineral under severe supply risk. The Pentagon dependence on GaN for modern radar and communication systems is now a recognized strategic vulnerability at the highest levels of American defense planning. This is not a temporary trade dispute. It is a demonstration of supply chain leverage that China can apply without firing a shot, affecting every American defense program that relies on GaN technology. The United States is not without its own capabilities in this field. Raytheon, now part of RTX Corporation, operates a dedicated GaN foundry in Andover, Massachusetts, producing high-power microwave circuits for military radars, including the SPY-6 naval radar and the Patriot LT AMDS ground-based system. Raytheon has reportedly achieved manufacturing readiness level 9 and technology readiness level 9 for its GaN technology, the highest possible ratings from the Department of Defense. The company has announced an $800 million investment to modernize its radar production facilities and expand automation at its GaN foundry. American engineering in GaN device fabrication remains highly advanced. Yet here is the critical gap. Raytheon can manufacture GaN chips. It does not produce primary gallium and depends on upstream suppliers for the raw material. The gallium must come from somewhere, and right now the majority of global supply originates in China. This creates a fundamental asymmetry. China controls much of the upstream production, from bauxite refining through alumina processing to gallium extraction. The United States controls the middle and end stages of chip fabrication and system integration, but faces a significant gap at the very beginning of the chain. This is the same structural vulnerability that has plagued rare earth elements for decades, now replicated with gallium. The Pentagon has launched a multi-pronged strategy to break this dependency, but each approach faces serious challenges. Scrap recycling offers the fastest short-term relief, with companies like Metallium in Texas and Element USA extracting gallium from electronic waste and manufacturing remnants using Defense Production Act funding. However, recycling cannot scale to meet the full demand of American defense and semiconductor industries over the long term. The volumes simply are not sufficient to replace primary production. The midterm solution involves building entirely new gallium extraction facilities from scratch. The Pentagon has provided funding to Atlantic Alumina in Louisiana to develop a facility capable of producing gallium as an aluminum byproduct, with targets in the range of tens of metric tons annually. Broader initiatives aim to stockpile critical minerals and build alternative supply chains, with early-stage efforts also underway in Germany, Australia, and Japan. But these projects will take years, possibly a decade, to reach meaningful production scale. In the meantime, the dependency remains. The long-term hedge involves looking beyond gallium altogether. DARPA has awarded Raytheon a contract to develop transistors using synthetic diamond and aluminum nitride, materials that do not depend on Chinese supply chains and offer even more extreme thermal tolerance than gallium-based compounds. If successful, these non-gallium materials could eliminate the choke point entirely for future radar and electronic warfare systems. This is a high-risk, high-reward bet that will take years to mature. Raytheon has also licensed its GaN on silicon technology to GlobalFoundries for commercial and dual-use infrastructure production at Fab 9 in Vermont. This partnership is significant because it grows GaN layers on standard silicon wafers rather than expensive silicon carbide substrates. Using silicon as the base material enables mass production at lower cost on existing 8-inch fabrication lines. This approach is considered crucial for future 5G and 6G wireless infrastructure, where high-frequency signals require the power density of GaN, but demand the cost structure of commercial semiconductor manufacturing. It represents an attempt to secure American leadership in the commercial applications that will fund the next generation of defense technology. The supply chain pressure is already affecting American military modernization timelines. While China has launched GaN-powered satellites capable of persistent wide-area surveillance, the United States continues working to integrate GaN technology across its existing platforms. The F-35 fighter radar upgrade to GaN-based systems has faced delays, though these stem from multiple factors including software integration and testing schedules rather than gallium supply alone. The broader point is that American defense programs must now navigate material uncertainty that did not exist a decade ago. The comparison reveals a strategic asymmetry. China has demonstrated mastery across the full stack, from raw material production through chip fabrication to end system integration and deployment. The United States retains formidable capabilities in chip design and system engineering, but faces a bottleneck at the raw material level that constrains its ability to compete in the very technologies that will define 21st century military superiority. This is not a criticism of American engineering capability. It is a consequence of allowing critical raw material supply chains to concentrate in a single geopolitical competitor. Lutytance 401 is more than a satellite. It is a symbol of a larger shift in the global balance of technological and industrial power. The ability to build a geosynchronous SAR satellite requires mastery of semiconductor physics, microwave engineering, space systems integration, and raw material supply chains. China has demonstrated progress across all of these domains simultaneously. The United States, despite its formidable technological base, has allowed a critical bottleneck to form that now constrains its ability to compete in next-generation surveillance and radar technology. This situation was not inevitable. It is the result of decades of supply chain optimization without strategic redundancy and a failure to recognize that control of raw materials is as important as control of intellectual property. China recognized this connection early and built its dominance deliberately. The West is now playing catch-up in a game where the rules, the materials, and the timeline are largely set by its competitor. Lutytance 4001 observes from 3D 6,000 kilometers above, a silent indicator of who currently holds the high ground in a technology that is reshaping global security.